Hello everyone. So in this video, we're going to talk about anatomy of smart contracts. Now let's just see how it goes ahead. First, you guys will be seeing up a program on the screen, right? A program that is Hello World, right? So that's super simple, but also super important. The Hello World program is generally a program when we start coding up in programming languages, that is the first program we generally learn to code, right? So that same goes here. Now that we are going to code up in Solidity, the first program that we're going to take up is Hello World, right? So the first line that says SPDX license identifier MIT. This line defines the license type of your code. And we have MIT's license that is most open, most permissive out there, right? Second thing we come across is pragma solidity greater than or equal to 0.7, 0.0, lesser than 0.9, 0.0. So this line is like setting the rules up for your compiler. It tells which versions are allowed to compile this contract. Here we are saying the code will work with any solidity version from 0.7.0 up to 0.9.0. Think of it like setting up a range that outside this range, the code is not going to be compatible to compile. Then we define a smart contract that goes by contract hello world. So in Solidity, your contract is similar to a class in other programming languages where you have functions, where you have data. And that is what we combine together variables and functions and we call contract in Solidity. So here our contract name is hello world, very simple, very classic. Then we have your string type. String public greet is equal to assign the value of hello world. So here we have declared a state variable. Now what are state variables? How am I calling this a state variable? This is something we're going to learn forward. Its data type is string. And the keyword public means that anyone can read it directly from the blockchain without needing to call up a separate function. So when we deploy off this contract, it stores hello world on the blockchain because it's a state variable. So it's not temporarily stored, but it is permanently stored in the blockchain because anything that's on the blockchain is permanent. And anyone can view it, proving that the contract works. Coming to second program. Pragma solidity, the bold lines I'm talking about because the bold lines are the code lines and the else are just the comments added. So you please take care of the bold lines because I'll be reading up the bold lines and then giving you the version of the commented lines. So pragma solidity caret 0.5.10. So this line again specifies the version of solidity where your code will be compatible to compile. And the caret symbol means any compiler version that is greater than or equal to 0.5.10 but also lesser than 0.6.0 will compile the code successfully. Then again we have the contract hello world. Remember, a contract in Solidity, as I told before, it's just what functions and variables put together. It contains both data called state variables and functions that define how that data behaves. Once deployed, this contract will live at a unique address on the Ethereum blockchain. The addresses we're going to talk right in this video, but in a short time. Then we have your string as public message. So here we declare a state variable of type string called message. Since it's marked as public, anyone can view it directly from outside the contract. And Solidity automatically creates a getter function for it, so we don't need to write one manually. Then we have a constructor function, which runs only once when the contract is deployed. It takes a parameter called init message, that is initialized message, and stores it in our state variable message. So you take up a variable init message and then store it in our variable message. So whenever you deploy the contract, you can actually pass in your custom message and that will get stored on the blockchain as your initial value. Right? Just think of it like getting a default message and setting it up the moment your smart contract is born. So this is a public function that allows us to change the stored message later on when we have their update function, you see. So if the contract originally said hello world, you can now just change it to hello blockchain. Anything you can make the change to. The keyword memory means the data exists temporarily. And if the keyword memory is not there, it means it's a state variable. and not a memory variable. But when you have the keyword memory, it means it's a memory variable. It's not stored permanently until we assign it to the state variable. Smart contracts. So what is smart contract? Smart contract is a program that runs at an address on Ethereum. They are made up of data and functions that can execute upon receiving a transaction. So data represents the contract state or variables, and functions define how the data can be changed, how the data can be accessed. Make sense? So when you store now the data, any contract data must be assigned to a location. That location can either be in your storage or be in your memory, right? Now, if that is in storage, it is permanent. Anything that is there in storage is permanent, and if I have to modify a storage, modify a variable in the storage, it is comparatively very hard because it is in the blockchain, right? So your storage is the permanent memory of your contract. It's stored directly on the blockchain. When I say it's stored in my, when I say it's stored in the storage app, that means once you change a value in storage, it stays there forever unless you overwrite it with a new one. But writing to storage is expensive because you're literally updating blockchain data. And when I talk about memory, memory is used during the execution of a function. So after the function, after the contract, smart contract has been, completed its execution, that does not exist. That is just now of no matter, right? Because its life cycle is only alongside the smart contract. Once the smart contract is completed, the it the variables in the memory are lost. So once the function it finishes running, the data disappears. And using memory hence is much cheaper than writing it to a storage, because writing to storage is actually writing on the blockchain. So let's talk more about storage. Persistent data is referred to as storage and is represented by state variables. So if you're not putting memory alongside your variables are state variables. And it's persistent data. The data is actually going to stay in. Even if your contract has been completed, it is going to stay in. That contract has been completed means your function has already run up, but this data is going to stay with you. These values get stored permanently on the blockchain. You need to declare the type so that the contract can keep track of how much storage on the blockchain it needs when it compiles. So you need to give unit uint store data means that is not unsigned int. You don't have to keep that in mind, but uint you know how much bytes are are allocated to uint, and that is when you know how much that is when you give your all the allocations of your state variables. You do it that way that you know how much storage your program needs, your smart contract needs when it has to be compiled. So this is what you need to make a beforehand allocation to data, right? In storage, your types include boolean, integer, fixed point numbers, fixed size byte arrays, dynamically sized byte arrays, rational integer literals, string literals, hexadecimal literals, enums. So in Solidity, an address is a special data type that can hold an Ethereum address. And each Ethereum address is 20 bytes, or in the SIG, 160 bits. You can think of it as the unique identity of an account, maybe, or smart contract on the Ethereum network. Just like every house has an address allocated to it, every flat has a building, every flat has a floor allocated to it. Just in the same way, your Ethereum user or contract has an address where others can send tokens or interact with their functions. An address in Ethereum is always shown in hexadecimal notation, and it starts with O0x. Now, if any of the given thing is starting with 0x, you know what is going to follow is actually a hexadecimal notation of the address, right? The address type comes in two large identical flavors. So what the thing is, not all addresses are created equal. Some addresses can receive Ether and some cannot. And that's where the difference between address and payable address comes in. So in Solidity, we have two largely identical flavors of addresses that go by address and that go by address payable. If I talk about address, it simply holds your 20 byte Ethereum address. But if I'm talking about the address payable, this one holds an address, but it can actually receive Ether. So basically, an address payable can use special functions like transfer, like send, which actually move Ether on the blockchain. The reason for the separation is safety. Not every address is meant to receive Ether, and if you send your Ethers to an address that is not supposed to be receiving Ethers, your Ethers are lost. Now you cannot just retain them back, right? That's why Solidity requires you to explicitly mark an address as payable when you intend to send it Ether. So coming to balance and transfer and then send. The code part that you can see here, address payable X is equal to payable 0x123. We first define X as a payable address, meaning we can now safely send ethers to it. Then we define my address. And now this is the address of the current contract using address. Okay. This, when you mention, it's the current contact using current contract, right? Now this simple conditional statement check. If X has less than 10 WEI, what is WEI? WEI, what cent is to dollar is WEI to Ether. As far as I remember, I think one Ether has 10 to the power 18 WEIs. So WEI is basically the smallest currency token of Ether, right? I'm not really sure about the number, but I believe it's one Ether is 10 to the power 18 WEIs. Okay. So if X has less than 10 WEI, and the contract's own balance is at least 10 WEI, then transfer 10 WEI to X. So now what is the contract statement? It says, I am the sender. My address is the sender. Payable X is which can receive ethers. Okay. X is the address, which is the payable address. So payable address means it is safe to send ethers to a payable address. So X is a payable address and my address is my address, the sender's address. So if I have more than 10 WEIs and at the same time X that is receiving has less than 10 WEIs, please send 10 WEIs from my address to X. Make sense? That is what is mentioned. Please transfer 10 WEIs in that case. And just like that, you've executed a secure transaction from one address to another, all within your smart contract. Make sense? So how did we see? Now you'll say, what is balance here? Because I've not defined balance anywhere, right? So it is actually a balance. The balance is actually a property that tells you how much ether in terms of WEI a particular address holds. And to actually send ether, we're using the transfer function. So now there is a difference between transfer function and send function. When you call transfer, what happens is Solidity automatically sends the specified amount of ether to that address. And if this transaction from my address to X fails for any reason, it throws an exception and reverts the transaction. Now let's say in between some problem happened, right? And I could not complete this transaction. So what my function is going to do, what transfer function is going to do, it is going to throw up an exception and revert the transaction back. So transfer is the safer option because it actually reverts the transaction if anything goes wrong. And then you also have a lower level way to send either, it is send. And if this is the thing, it works similar to transfer, but there's one key difference. If something goes wrong, send is not going to throw an error. Instead, it is just going to simply return false. And then you will have to manually intervene and do the needful. So when I talk about storage, we've talked about this before as well. Storage is a key value store that maps 256-bit words to 256-bit words. Key value, key is also 256-bit word, and your value is also 256-bit word. It is not possible to enumerate storage from within a contract. It is comparatively costly to read and even more to initialize and modify storage because storage is directly done on the blockchain itself. Because of this cost, you should minimize what you store in persistent storage to what the contract needs to run. So, whatever you're storing up in the persistent storage is something that you always need. So make sure that if there is some caching or if there is some temporary calculations, derived calculations, aggregates, you're keeping them outside of the contract in your memory. A contract can neither read nor write to any storage apart from its own. Then coming to memory, Values that are only stored for the lifetime of a contract's function execution are called memory variables. Since they're not stored permanently on the blockchain, they're much cheaper to use. And please, if there is something that your function is going to need forever, irrespective of its life cycle, please keep that in storage. And if we have some derived results, some of the other things that are actually on the way things, please keep them in your memory. Memory is linear and can be addressed at byte level, but reads are limited to a width of 256 bits, while writes can be either 8 bits or 256 bits wide. Memory is expanded by a word, so if you go outside 256 bit, you get another 256 bits added, right? At the time of expansion, the cost in gas must be paid. Now, what is your gas? Gas is actually a fuel on which Ethereum runs. You can just take it in this way. So, every function that we're calling, every memory address that we're using, it has an associated gas value. And we need to pay them all in terms of your transaction cost. Make sense? Memory is more costly the larger it grows. So, it's like your electricity bill, you may say. If you're using until this unit, you're going to pay this much X amount per unit. But if your consumption increases this threshold, then it is going to be X plus 10, let's say, per unit. Make sense? Now let's come to stack. So your Ethereum virtual machine isn't actually a register-based machine like your computer CPU. The computer CPU, as if you all know, remember well, it's register-based, right? Instead, your EVM, your Ethereum virtual machine, is a stack-based machine, meaning that all computations happen on a data stack. The stack can hold up to 1024 elements, and each element is 256 bits wide, 256, 256, 256, and such that I can store 1024 elements. All arithmetical, all logical, all functional operations happen right here. And the key is, because it's a stack, you can only directly access the top elements of the stack. You can copy, you can swap the topmost 16 elements, but if you want to go deeper, if you want to, reach to an element that is deeper in the stack, you will have to pop off elements until you reach it. So what do you do in a pop off? You make use of the other two things that you have in with you. And that is what makes it more judicious use, right? So you do what? You keep moving data between stack, between memory, between storage to manage it efficiently without breaking any of their limitations, without breaking the stack limitations, without breaking the memory limitations, and without breaking your storage limitations. So while your stack is lightning fast, it's limited in size and temporary, making it ideal for executing operations but not for storing large or persistent data. Because to store persistent data, you need to make sure you're using your storage. Then coming to your instruction set, the instruction set of the EVM is kept minimal in order to avoid incorrect or inconsistent implementations, which can actually cause consensus problems in the longer run. All instructions operate on the basic data type, 256-bit words, or on slices of memory. The usual arithmetic, bit, logical, and comparison operations are present. Conditional and unconditional jumps are possible. Furthermore, contracts can access relevant properties of the current block, like its numbers, like its timestamp. I hope all these are good with you, right? Important thing, message calls. So what are message calls? Just like humans interact, humans communicate with each other, contracts do so, right? Contracts communicate, and if they communicate, they do so through message calls. A contract can call another contract or even send ether to an externally owned account. And if they're doing so, each message call that they're making for the same thing, it includes source, target, data payload, ether, gas return data, right? Every transaction starts with a top level message call, and that can trigger a chain of further calls. So if I call a main function, it has many inbuilt not inbuilt functions, but in present functions. And my main function can make a call to them, and it could actually cascade down, right? If a called contract runs out of gas or throws an error, Solidity will do what? Solidity is known to revert that inner call by default. So this process is known as exception bubbling. Ensures that if something goes wrong deep in the chain, the entire transaction is reverted safely. I hope you get this off. Environment variables, there are some special global variables that are primarily used to provide information on the blockchain or the current transaction. We have block.timestamp, message.sender, and many more. Coming to control structures, with this slide, I'm going to end up this video lecture. But if you have any doubts, please make sure you're using the comment section. You're using the G forms attached if you want any reclarifying concept videos. And yeah, if you're getting up the video, if you're extracting something useful out of the video, just go in, like the video, and subscribe to the channel because the playlist is still growing. Okay, so we'll start with control structures now. Most of the control structures known from curly braces languages, the languages which we, if and then we used to start a curly brace, write everything, and this close. If condition and then curly brace inside what is to be executed and then curly brace close. That is what your curly brace languages are. So also in Solidity, we have if, else, while, do, for, break, continue, return with the usual semantics known from C or JavaScript. Nothing new for you. Solidity also supports exception handling in the form of try-catch statements. Your C also supported it, but only for external function calls and contract creation calls. Errors can be created using the revert statement. Parentheses cannot be omitted for conditionals, but curly braces can be omitted around single statement bodies. Same in C. So if you're writing if the conditional bracket, you write it in the, what do you say, you call it in parentheses. In parentheses, you write what the condition is for the if statement. That cannot be omitted. But what you're writing in the body of if statement, if that single line, if this, print this, then for that print statement, the conditionals can be executed, the conditionals of curly braces. Not anything to do with parentheses. This has to be there. If there is a if, there has to be a condition, right? And if you have two statements inside your if block, then your curly braces can also not be omitted, right? And also, just to mention, there is no type conversion from non-boolean to boolean types as there is in C and JavaScript. So if I write if one and write print hello world, and if one would be taken as if true, right? But here you cannot do that, as it is given if one and then your body of the if statement, it is not valid in Solidity. So with this, I'll take your leave. In the next lecture, we're going to see functions. Bye-bye. Have a good day.